Go ahead.
What happened was, 20 years later, Einstein comes along and says, well, Michelson and Morley showed there was no luminiferous ether, therefore, light has to be a particle to get through space. Well, is space a space? There was a dude who won a Nobel Prize called Alpha, and that was around 1970, 71, somewhere around there. And in 1937, see the difference between him and Einstein? Alpha is saying, when we actually send stuff out to space, we're going to find out it's full of charged entities. Einstein, of course, he's doing it before, but, I don't think he ever repented or anything like that. He said, space is just, it's empty space. And then Alpha, he's the one who's prophetic. He's saying it's going to be full of charged particles. Well, you see, if you've got charged particles out there and they're moving, and there is movement relative to things relative to each other, guess what's generated? Something spooky. And this dude was saying here, this dude here, was saying, like this luminiferous ether had to be spooky, because you could see planets were moving through it, through space, and they weren't getting slowed down. If you're cycling through something or something like that, or wind's blowing you, you're going to get buffeted, you're going to get slowed down if you're running into the wind, right? And that's what should be happening if there's something like a luminiferous ether out there, that is made up of material, it has a mass. It's going to slow the planets down, and they're not getting slowed down. Therefore, it can't exist. It's got to be spooky, right? Well, guess what? It is spooky. And it was discovered by people like Ørsted and Faraday. Long time ago. Almost 200 years ago. 200 years before this idiot. And you know what it's called? It's called magnetic fields. See, that's what happens when you get charged in outer space. This thing was found. Alpha was predicting it in 1937, and then they found it once they started sending up Sputnik and its successors, starting in 1957. They're finding out space is full of ionized ions. So there were atoms that have been pulled apart into the constituent entities. And see, the trouble is, they're moving. When they relative to each other, when they move, they generate a magnetic field. Have you ever seen a magnetic field? Have you ever brushed up against one? See, planets and moons and stuff like that they basically don't have a charge. That's the way they're perceived by scientists. And so when they brush up against the magnetic field, guess what happens to them? Nothing. When you stomp through a magnetic field, well, you've got some charge in you from your white corpuscles, but they're negatively charged, so on and so forth. But all told, like you're going to walk through. Have you ever walked through a magnetic field and said, geez, that's really slowing me down like a Chinook wind? Like it might bug us, we might hear some sounds and stuff like that, or whatever some people claim. And they're probably not making it up that they can hear the northern lights and stuff like that, right?
Well, some people are sensitive.
Yeah, exactly right. But it's not like walking into a Chinook wind. It's not going to slow you down. So, like this guy is saying what will happen with the planet. Magnetic fields are about as spooky as things it should get in science. Unfortunately, these guys are, they're going, magnetic fields, they're not even thinking about them. And then what they do is they dream up spooky, stupid, medieval kind of stuff. What the medium for light is, are you hearing, you astrophysicists? With the emphasis on ASS at the beginning of your names, astrophysicists. The medium for light is not the ether, it's many ethers. It's many media. And those media are called magnetic fields. They are what carries along a light. Carries along light from one place to another through so-called space. It's not space. It's full of electrical charge. And in a vacuum tube, it's not a vacuum. It's full of electrical charge. It's full of magnetic fields. So here we got it. This is what Einstein got wrong when he says rejection of black holes. So why do you have a black hole? Well, light is supposed to be a particle. And so if you get a massive enough gravitational field, not necessarily big, but massive, and very heavy, it's supposed to be so heavy that it can pull in on incoming light and not allow it to come back out. And so it ends up being a black hole. See, the light doesn't come out. Brilliant. But if you don't need light being a particle, there's no need for black holes. It's just a figment of these dudes' imaginations. So Einstein, of course, he's thought to have no imagination when he rejects black holes. And it actually follows. He's such a moron. It follows from his own stupid original idea of light being a particle. But so he was wrong about that, but ultimately he was right. So he's right, but for the wrong reason, right? So black holes, I mean, it's insane. You see, what happens is, in real life, when you suck stuff together, like at the center of the Earth, not even the center, you get pressure built on top of it, right? Pressure, pressure, pressure. What happens when you increase the pressure in real life on something? You know how a pressure cooker works? You increase the temperature, right? Mm-hmm. Yeah, that's what happens. So when you increase the pressure, then the temperature increases. Now, what happens when you increase the temperature on something like a metal? If you increase it enough,
It melts.
it melts. And then where does it go? You've seen convection currents inside boiling water, right? Are there convection currents inside the Earth? Darn tootin'. So that's what continental drift is, right? It's there's a drift on top, but that's just one of these convection cycles, right? So the rocks down there are basically, like plastic, and who knows how liquid. Well, they say in the core, the outer core, it's liquid. So that's what's happened, right? There's so much pressure from all the stuff on the outside scrunching down on this stuff. And this is just like a little bit below the surface when you're looking at the overall diameter of the world. The stuff is plastic, it's moving around, it's smudging around. So that's what happens. Ultimately, you squish it enough and it comes up in the form of
Geysers? Volcanoes?
Volcanoes and stuff like that. And sometimes they don't come all the way to the surface, So that's what the Sweetgrass Hills were like, right? They've actually been exposed. They came part of the way up and then they cooled enough and they stopped there, right? So they're called intrusions, right? So I think it's a granitic intrusion. So this is what happens in real life. In real life, if stuff gets scrunched down, it gets heated up and then it expands and it comes welling back up. You get these convection currents. That's what happens in real life physicists. So, like, you aren't really physicists, you're philosophers, especially you astrophysicists with the ASS at the beginning, and not AST, ASST. And same thing with you quantum physicists. We'll get to that next. Okay, Einstein's rejection. Einstein and gravitational waves. Well, like gravitational waves. What's gravitation based on? Is it based on mass, or is it based actually on the differences? When we actually look at the balance of things and the way it gets attracted down to Earth, this is one thing that Galileo didn't take into account. The way stuff gets attracted down to Earth, what gravitation is a way of sorting out things, not so much in terms of mass, but in terms of density. Okay? So stuff goes down faster towards the Earth, the more dense it is. It's sorting itself out with respect to the air, for example, that it's going through when it gets dropped towards the Earth. So something that's less dense, like a feather, is going to go down. There are other factors involved too. But let's say a bag full of feathers, it's going to come down more slowly because it's getting sorted out more slowly with respect to what it's coming down through. This is what gravitation actually is. When you look at it overall, when you're taking things like buoyancy into account. So here's the thing, what we've got is we've got waves that are associated with light, right? waves that are there and associated things. They're electromagnetic, they're electric waves, right? Or light waves or gamma rays and all this sort of stuff. There's a whole spectrum of these things. There's radio waves and infrared waves. They're on a huge spectrum based on their frequency. Well, the thing that would be different for gravitation, those things are based on things like electrical charge. And what we should be looking for when we're looking for gravitational waves, we should look for stuff maybe here on Earth instead of looking for black holes bashing into each other and sending out little blorps of sound that you need huge sensors to try and find and stuff like that. Instead of looking for the exotic, let's look for something that's a little more prosaic. And so light, it's maybe based on, the waves are based on differences in charge. How about something that's based on the differences in density? Is there a kind of wave that's based on differences in density? Oh yeah. What happens is when I'm talking to you, there's energy is expelled and it bumps air molecules, and what happens is you get a certain number of air molecules scrunching up together, and then behind it there's a rarefaction, and then scrunching up together, rarefaction, scrunching up together, rarefaction. So it's based on differences of density. Gravitational waves are sound waves. They're sound waves. Okay, so Einstein, let me think, gravitational waves, I don't think he was very friendly towards that. So guess what? He was right about that. The gravitational waves that these idiots are looking for, and they claim that they've discovered out there and stuff like that, gravitational waves are just sound waves. And anything else they discover out there is some other weird phenomenon. They're not coming from black holes bashing into each other. There are no black holes to bash into each other. There's some weird stuff happening out there, but they're not black holes and they're not bashing into each other. Cosmology and the cosmological constant. Okay, so Einstein was trying to come up with some stuff. And what he did was he did an ad hoc thing. Things weren't adding up for him. You know, like the whole thing is, if you're doing a math exercise for marks, and the numbers don't add up to what you know the answer should be, and you just add plus 22 to get the right answer. You know, that's why you're asked to show your work. You know, it's not just the answer. You know,
it's like Pauline's math. It's like, I don't know what I'm doing.
Ultimately, people do anything for marks, right? You know what I'm saying? Yeah, exactly.
Draw a picture.
Yeah.
Plus smiley face, please.
Yeah, please do. Yeah. So, Einstein was doing the smiley face for himself. He's sitting there fooling himself. It's, you know, Pauline recognizes what's happening, so it's not intellectual dishonesty, it's just hopeful, wishful thinking, right? You know, and we've all done it on mathematics, you know, like you're doing a test, and you're just going, oh, okay, I got to get something down. Yeah, here's Bozo. He wants to be a world-class expert, you know, like already been, you know, feted and touted and all this sort of stuff. I think this is something like 1917. So 12 years after he published these 4 groundbreaking papers, he still wasn't accepted really by the majority of scientists. But he comes up with a cosmological constant, which is basically, you know, like, it's funny because it's alliterative. Do you notice how that is? Right, cosmological constant.
Oh,
catchy,
nice.
right?
Yes.
Yeah. But what it is, the real alliteration is fudge factor. Fudge factor. That's what the cosmological constant is, right? So, yeah. So he's going along, and he was saying this is the greatest mistake of his life, and all this sort of stuff, because he wanted what's called a flat universe. I don't think he called it back then, but that's what it's called now. One that isn't expanding or contracting and stuff like that. So when Hubble Bubble comes up with the idea of expanding universe, you know, Einstein kind of says, geez, like I should have gone for a kind of a fudge factor that would have let me expand the universe and stuff like that. Nowadays, these guys are enthused about the cosmological constant again because they get enthused about the weirdest, wackiest things. Okay, cosmology and the cosmological constant and dark energy. This is again medieval thinking. Oxymorons don't exist. They're contradiction in terms. That's what oxymoron is. Strictly speaking, oxymoron, in Greek, oxy means sharp, moron means dull. The very term is an oxymoron, sharp, dull. And that's what these dudes are. They're sharp, dull individuals. But oxymorons don't exist. These guys are not sharp. They are morons. They're dull, right? So this is what happens when you get dark energy. Dark energy is energy that you can't detect, right? It's just out there. It's another fudge factor. What they've got is their equations, and their equations tell them, based on their assumptions, tell them that there's got to be a lot of dark energy out there. Why is that? Oh, it's to make their assumptions come out true. They're getting stuff coming in from outside. They're getting the not so much experimental evidence, but the experiential evidence coming in, and it tells them that according to their assumptions, there has to be some dark energy out there to explain it all. And what it should be telling them instead is, hey dudes, you should be going back to your drawing board, because what you've got is a contradiction, and not just in terms, contradiction in terms of what's coming in and what you guys are saying should be coming in. But no, that's not the way these guys think. These guys are the Sheldon Coopers of this world. You can't tell them anything. They're here to tell you the Sermon on the Mount. So, and dark energy, okay? So that's, I think, why they brought the cosmological constant back in. What Einstein got right, light quanta. So we were talking about that before. Those are photons. Now, here's more medieval thinking. I was mentioning the medieval, I guess it's true, not a suburban myth. There was this controversy. How many angels can you fit on the end of a pin? Okay, let's ask the physicist. How many light quanta, or photons, particles of light, can you fit on the end of a pin? An infinite number. Wow, that's amazing. Because quanta are supposed to be matter. They're supposed to be particles of matter. But you can fit an infinite number in a limited space. That's medieval thinking. And it's the sort of stuff that happens when you start assuming stupid stuff. It is when you apply Occam's razor to the idea of photons, you just say, there's no need for it. Get rid of that sort of stuff. Because what happens is when you start assuming this, you start running into problems. Then you start saying, well, in order to explain how light is, you have to have an infinite number of particles, allow for an infinite number of particles to be fitted into a finite space. Wow. No, the only way you can fit an infinite number of particles in a space is to have infinite space. So he got that right. He got that wrong. At any rate, I'll just keep going just for practice. Does God play?
We'll do that one next. You're gonna watch the disc.
Am I?
Yeah, you are.
Oh, the disc.
Yeah.
Oh, that's right. I actually started. Well, I know what I've read the book.
He's read the book. Right.
And I knew exactly what they'd be talking about as soon as I.
No, you have to watch the disc first, though.
I'll watch it just for entertainment. Yeah. But I know exactly. I've read the book and stuff like that.
I might have missed some.
And I know all of this garbage. I've gone through it. I've been going through it for more than 20 years. It'll be about almost 25 years reading this garbage. And this guy's just, at the end of I hope it's the end of a long line of apologists for Einstein and accusers as well, because Einstein, according to these bozos, got so many things wrong. What we'll be looking at is stuff like quantum garbage. So that's what this thing is about. It's about
the next disc?
Quantum.
Yeah.
So that's why it starts with light quanta and junk like that. But yeah, he's supposed to have been, along with Max Planck, the beginner of quantum theory, and he's a bad guy because he wouldn't accept the logical consequences of the idea of light being a particle. So, yeah, we'll see what it's like.
Okay.
I know exactly what it's like.
We're gonna listen to the next disc maybe tomorrow or the next day.
Yeah, some next day probably.